Hey guys, welcome back. It's Worth. As you can see, there's like a couple of new changes. Number one, I have this microphone. My parents got it for me like over break, and it's been pretty useful. It's been pretty cool to mess around with. Also, as you can see, I'm not in my dorm. I'm not in like a random study lounge. I'm actually back home, and I will be at least for the next 2 weeks. Anyways, I decided that I wanted to temporarily step away from just, oh, let's mock this VC test, let's mock this TMSC test, let's mock this UIL test. And I said try to, spread my knowledge, which I think was one of the main goals I wanted going into this, like creating this channel. So I've created, or at least constructed, a two-part series of, in theory, everything you need to know about calculus for UIL. So I split this into two parts because I originally was going to do this in one part, and then I talked with a friend, and then we are like, maybe two parts is, or maybe one combined video is gonna be like 2.5 hours or something. It's gonna be way too big. So I split this into two parts based on like mostly like the BC calculus curriculum. One half is like differential calculus, which is this video, and the other half, which I'll finish probably at some point within the next week, is gonna be integral calculus. So hopefully y'all enjoy, and I'm gonna split I'm gonna split the video down below, kind of just like the main chapter, so you can feel free to just skip through. Just a couple of notes, I guess. Don't use this if you're trying to like learn calculus for the first time for the purpose of BC. Because if you're doing this for the purpose of BC for the exam, I think it's not going to work. I think this will be a good video if you already taken BC and need the review for UIL, or you're like last minute prepping for like the BC exam, just need like a whole review, or you're just only learning this just for the purpose of UIL, and you don't really care as to whether you do well like in an actual classroom environment or not. This is just kind of a holistic review that hopefully gives you enough of an idea that you can solve a lot of different problems and stuff like that. And then if y'all have any questions or any topics that you think that I may have forgotten that are really important, feel free to just like comment those below. I'll try to see if I can incorporate those, either answer your questions or possibly make new videos that are gonna just be off to the side that go further on these topics and whatnot. So yeah, hope y'all enjoy, and I don't know, have fun. Before we kind of start diving into all the stuff about derivatives, I think it's really important to really quickly just touch into what a derivative is and kind of how it's defined. So easiest way to look at this is just starting with two types of equations, one linear, one not linear. So if we make a linear equation first, we can say that if, for instance, we have this point 1 comma 3, and then this point, let's say 8 comma 17. If I want to find the slope of this, I just use that old rise over run formula. This be 8 minus 1 equals 2. And I could use this slope to not only make an equation for the line, but I can say that no matter what 2 points I pick, I'll always get 2 because the slope everywhere is 2. It's always going to increase 2 in the y for every 1 increase in the x. Now, the issue comes with, here, let's erase this with real quick. The issue comes with, what if we don't have a linear equation? What if instead we have an equation that kind of looks like that? Right? I know you're not normally going to see an equation as crazy as this, but just for explanation purposes. So what I'm going to do here is I'm going to define 2 points. Let's say we have x1 and we have x2 here, right? And I want to find what is the instantaneous slope at x1. How much is y increasing for every increase in 1 in the x right at x equals x1? So what I can do is, if I have these 2 points here, I can draw this kind of line connecting them, and I can say, oh, the average change of this function, we'll call this f of x, the average change of f of x from x1 to x2 is equal to f of x2 minus f of x1 over x2 minus x1, the change in y over the change in x. And you can see here that the change that we have here isn't really close to the exact change at x1. It is positive, but it's not really close to what it should be. So what I'll do now is, let's define a new point, right? Let's say we have x3 right here, right? And I draw this new line here. Then I say, okay, let's calculate this new distance between x3 and x1. And we'll notice that as I get closer to x1, this slope is going to get closer and closer until we eventually get what we call a tangent line, where it just hits it right at that kind of sweet spot, if you like. Right? So how can we write this in a more mathematical, kind of formulaic definition? What we do is we use the limit. So let's define x2 as x1 plus some distance h, right? We're decreasing h, and we're trying to decrease it as much as possible to where x1 and x2 are basically the same, but not exactly, because otherwise our denominator would be 0 and we can't really divide, right? So we say that we're trying to figure out this kind of equation right here. So let's rewrite this with the h in here. So we have f of, and I'll replace x1 with x, just so it matches the form we'll regularly see it. We kind of see something like this, right? And since x3 minus x1 or x2 minus x1, that's the distance between the points, we can just replace that with h here. And what we can see is that if we take the limit of this expression as h approaches 0, this will equal the slope, or give some kind of function or some number or something that represents the slope of f. And we call this the derivative of f. And we can see this as f prime. We can see this as d over dx of f, or df over dx. These are the same thing. These are the two main forms you'll see it. Either this form right here with the kind of apostrophe, or with this d over dx kind of thing. So one example of how we can use this is, let's say we're trying to find the derivative function of the function f of x equals x squared. If I take our equation that we just wrote and we plug it in, we get x plus h whole squared minus x squared over h. We rewrite this as the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared, all of that over h. And then, because of the canceling we can do, we can remove this x squared and this minus x squared. This h can divide this and this out. And we're going to end up getting the limit as h approaches 0 of 2x plus h, which is just equal to 2x. So therefore we can say that df over dx is equal to 2x. So for instance, let's say we have the point 3 comma 9 that exists on here. We can say that f prime of 3 is equal to 2 times 3, or 6, and that the tangent line will be y minus 9 equals 6 times x minus 3, or y equals 6x, this would be minus 9, just like that. So you can see that with this limit kind of definition over here, you'll usually never really see this a lot, other than maybe when you first learn it. You may occasionally see it thrown here or there, but there's very few cases where you actually need to use this limit definition. Nevertheless, I think it's pretty helpful just to kind of start with the basics, as like how we're getting a derivative and how all the rules we're going to eventually cover are going to use this basic definition right here and come with so many rules and all the different applications that eventually come with it. All right, now it's time to cover the different differentiation rules. So what we're going to start out with is the most basic of the rules, known as the power rule. And this works for all functions in terms of x to the n, similar to how we said that the derivative of x squared was equal to 2x. Instead of doing the whole expansion thing, what we can do is this simple process. If we move this n over here and then subtract 1, we end up getting, I'll make an arrow instead, we end up getting n times x to the power of n minus 1, and this is our derivative. For instance, the derivative of x to the 5th is 5x to the 4th, and the derivative of x to the negative 2nd is going to be negative 2x to the negative 3. So it works with both positive and negative numbers. Then, after the power rule, we have, I guess, our exponentials and our logarithmics. Let me just remove this, because I don't want to scroll too much. you have exponentials that are logarithmics. So this would be e to the x, a to the x, ln x, and log base a of x. And in this case, for both of these things right here, we're assuming a is some number that's not equal to e, because if it is equal to e, we just use the left two things. So e to the x is unique because its derivative is actually itself. Then the derivative of ln x is 1 over x. The derivative of a to the x is a to the x times ln a. And you'll see when a equals e, this just becomes 1, that ln a part. And then the derivative of log base a of x is going to be equal to 1 over x times the ln of a. And then, yeah, this ln of a part, when a is equal to e, it becomes 1. So then we just reduce to e to the x and 1 over x, respectively. So those are your, I don't know why this isn't selecting. So those are some of the things you have to memorize. And then one more thing that is really important to memorize is the different trig derivatives. So that would be the derivatives of sine x, cosine x, tangent x, cosecant of x, secant of x, and cotangent of x. So I'm just going to write all these down real quick. We have this. Right? So these are the derivatives, and these you do have to completely memorize, but there are a couple of things that you can additionally remember and some additional cool tricks that you can realize. For instance, the derivatives of sine and cosine actually form a cycle. The derivative of sine, as we said, is cosine, and the derivative of cosine is negative sine. From there, we say the derivative of negative sine is negative cosine, and the derivative of negative cosine would just be sine again. So it forms a cycle between sine, cosine, and negative cosine, which is really helpful because that way we don't have to worry about like other issues. And especially with integration, this cycle becomes helpful because we can go both ways very easily. One other thing is tangent x and cotangent x, both of them have this kind of square term here. And then you'll notice how some of our functions have a negative sign. All those negative signs happen to be on functions whose names begin with C. Kind of just a random thing that happens by coincidence, I think. But again, another really good thing to know. Now, that's like, I think, the last major thing you really have to memorize. So it's time for all the other rules, where instead of having one function like just the derivative of sine or the derivative of x squared, what if instead I wanted the derivative of x squared times the ln of x? There's a couple of different rules that we can use for this. First of all is our sum and difference rule. And what this tells us is that if we have two functions, let's say we're trying to find the derivative of sine x plus ln x, what this tells us is that we can just differentiate each term and then just add them. So we just take these derivatives and add them together like that. And then if this were to change to a minus sign, that same logic would apply. However, this basic idea only works for sums and differences, where we can just take the derivatives individually and add them or subtract them. For multiplication, we have to use what's called the product rule, which states that the derivative of f times g is equal to f times the derivative of g plus g times the derivative of f. So for example, let's say we're trying to find the derivative of sine of x times, let's say, e to the x, right? Normally I write it the other way around, but it's fine. So we can say that this is equal to sine of x times the derivative of e to the x itself plus e to the x times the derivative of sine of x, cosine x, just like that. Our quotient rule is more complicated. It follows the same idea that you can't just take the derivative of the top, take the derivative of the bottom. But what our quotient rule is going to state, quotient, I'm like adjusting my mic along the way. Quotient rule is that the derivative of f over g is going to be equal to g times f prime minus f times g prime over g squared. And a way you can remember this, I was taught this in physics, which is after I learned the rule, but I still use this a lot whenever I need to use the quotient rule, is you take low times the derivative of high minus high times the derivative of low over low times low. So low d high minus high d low over low low. Sounds really silly, but it's always worked for me. So for instance, if we're taking the derivative of, let's say, sine of x over x, this is equal to x times cosine x minus sine of x times 1 over x squared, just like that. So that covers each of our four main operations, addition, subtraction, multiplication, and division. But what about if we had the derivative of the sine of x squared? Now for this, we don't have two functions that we're adding, subtracting, multiplying, or dividing. This is a composition function. So to differentiate a composition function, what we say is if we have the derivative of f of g of x, actually, let me do this in a different color. Although it'll be a lot of switching, but it's fine. So we have f of g of x. This is going to be equal to f prime of g of x times g prime of x. So in our example here, our inner function, that g of x, is going to be x squared, and our outer function is sine of x. So we'll take the derivative of sine x, which is cosine x, and replace that x with our inner function. So this would be cosine of x squared times the derivative of that inner function. So that would be 2x. We could go with like a way more complicated example, which would be like d over dx of, let's say, like sine of x squared. Let me think. Let's just say this squared, right? So we're taking x squared, we're plugging it into sine x, and we're plugging that into x squared. This is kind of the same thing, but it's just almost like the layers of an onion. We have to start from the outer and go inner. So for this, we would take the derivative of our outermost function, which is 2x. So we take 2 times that sine of x squared, and we're going to multiply it by the derivative of sine of x squared. In this case, we already calculated it. So that's just cosine x squared times 2x. But if you weren't given this thing in the first place, you'd have to do multiple chain rules. Okay, so there's that bit. Then one more thing we can cover is, or I guess two more things. This is one of those things, which is the derivative of our inverse trig. So for instance, let's say we have the derivative of the arc sine of x. Right, how can we do this? It's easier, obviously, to just memorize these following derivatives. Here, let me write these down first. So this means negative 1 over 1 minus x squared. And then this is 1 over 1 plus x squared. Another way we can do this is say, okay, if y is equal to the arc sine of x, then the sine of y must be equal to x, where y is an angle. And if we draw out this kind of right triangle here with our angle here, we can draw a triangle that looks like this. And this works because if you take the sine of y, it's opposite over hypotenuse. So x over 1, that gets you x. And now let's differentiate each side using the chain rule. On the left side, we have cosine of y times the derivative of that inner function. And this is equal to 1. And when we solve for the cosine of y, we're going to end up getting 1 over this cosine, which just ends up being square root of 1 minus x squared. And then you would just repeat this process if you wanted to figure out, okay, what is arc cosine, or what is arctangent's derivative. And the very last thing to cover is something that something that doesn't come up in BC calculus, but it is good to know. I kind of like the idea behind it. And this is something called logarithmic differentiation. And how logarithmic differentiation works is we take the function y of x and we take y of x equals something. We're going to take the natural log of each side and then differentiate it. And this helps us a lot with trying to find the derivative of a complex function. So for instance, let's let y equal x to the x, right? Now with all our rules, we don't really have any easy way to do this with chain rule or the exponential rules or anything. So what we're going to do is let's take the ln of each side. So if y is equal to x to the x, then ln of y is also equal to ln of x to the x. And by our log rules, ln of y is equal to x times the ln of x. Now, if we differentiate both sides, we get 1 over y times dy over dx, which comes from chain rule, is equal to x times 1 over x plus ln of x times 1. Then we can just multiply that y over and substitute. This is equal to x to the x times, this is just 1 plus ln x. And then we get the derivative for x to the x without having to worry about how complicated this function could be. And those are basically all the different rules you need to know for differentiation. This next section is just going to cover some of the many different uses of how we can use a derivative. So one of the first examples is going to be this rule called L'Hopital's rule. I'm not French, so I probably pronounced that wrong. I don't really care. And what L'Hopital's rule states is, let's say we have the derivative as x approaches c of f of x over g of x, right? Now let's say when we plug this in, we get that like the fraction 0 over 0 or plus or minus infinity over infinity. If one of these two things happens, then we have what's called an intermediate form. And what L'Hopital's rule states is that if we can differentiate both f of x and g of x at x equals c, so if we find the derivative and c exists in the domain of it, and the derivative of g at c is not 0, then so we want to make sure that g prime of c, or like the limit as x approaches c of g prime, is not 0. This is another condition. I meant to make this a different color. Can I make this red? It's fine. Oh, I can actually. Here, let's make that red. Okay, there we go. Okay, so if this is true, then we can say that this is equal to the limit as x approaches c of f prime of x over g prime of x. And an example of this is, let's say we have the limit as x approaches infinity of ln x over x, right? If we try to evaluate this top function, ln x, kind of just looks like this. So it's going to approach infinity. And if we plug in x here, this is also going to be infinity. So because this is our intermediate form, we can go ahead and differentiate the top and bottom and keep this x approaches infinity. We take the derivative of the top and divide by the derivative of the bottom. And what we're going to realize is the limit as x approaches infinity of 1 over x is just going to be 0, right? It's going to be 1 over a super duper big number. And we divide that by 1. And that means that we get 0 as our limit. L'Hopital's is something that, in BC calculus especially, you'll tend to see this a lot. One important thing to note, though, is just to make sure that if you see some limit of a ratio of a fraction, not a fraction, sorry, a function over another function, a rational function, that you may not necessarily need to use L'Hopital's, because if you plug in values and you don't get 0 over 0 or infinity over infinity, you won't be able to differentiate and get the same answer. So if I'll use a really silly example. Let's say I had the limit as x approaches 1 of 2x over x squared, right? You notice that we can plug this in normally, and we would end up just getting, here I'll write this to the side, we would end up getting 2 over 1, which is 2, right? In this case, what happens is if we accidentally do differentiate, we'd say the limit as x approaches 1 of 2 over 2x, and when we plug in x equals 1, we end up getting 1. And that, as we just realized, is wrong. So very important to recognize what that you get that intermediate form, or yeah, that intermediate form first, and then use L'Hopital's rule. So the next thing that we're going to cover is called the IVT, the intermediate value theorem. And note that for BC calculus, it's very important that you know like the exact definitions of when these used. I'm going to be pretty loose on this. The general idea of the intermediate value theorem is, let's say we have a function here, and this is really easy to see visually. And we have a function that kind of just looks like this. Let's say we have this point. This is x equals a, and we have this point here. This is x equals b, right? If we say that this function f of x here, if f of x is a continuous function on this interval from a to b, then for all c, I'm not going to write this with the discrete method. What this basically says is that for all c such that a is less than c is less than b, or sorry, f of a is less than c, which is less than f of b. Let me write this more cleanly. So for all c that exists basically between these y values, there exists some x such that f of that x, I'll mark it x1, is equal to c. Now what does that mean? So let's say we have this point here. Let's say this is 2, and then this is 4, this is 1, this is 3. What we can say with IVT, for instance, is that since we know f of 1 is equal to 2 and f of 3 is equal to 4, then since this is a continuous function, we know that f of x1 equals 3 is going to exist. There's going to be some x1 where 1 is less than x1 less than 3, such that it has to equal 3. And remember, since this is continuous, this kind of makes sense. Because to go from 2 to 4 while being continuous, we have to pass this line at some point. And whenever we pass that point, we'll find an x value such that it's equal. So I think that's honestly about it. There's not really much of a, like an additional example I really need to provide. That's kind of the idea behind IVT. Yeah, IVT. So that's the intermediate value theorem. And we have another theorem kind of similar to that, which is known as the mean value theorem. And this one is kind of similar, slightly less intuitive, but what this states is that if f of x is continuous and differentiable on the range a is less than x is less than b, there exists some value c such that a is less than c is less than b, such that f prime of c is equal to f of b minus f of a over b minus a. So in other words, if we take 2 points on the function, then we say there has to be a point between that function where the instantaneous slope there is going to be equal to the average rate of change from a to b. And I don't really have a good example of this, so I had to use Google a bunch. But a good example of this, I don't really have anywhere to move this, I'll just keep it here, I guess. A good example of this is talking about speeding, right? So let's say we have a function x of t that marks your position. And we say that x of, like after 1 hour, your position is at 50 miles. And at 3 hours, your position is at 130 miles, right? And let's say, I don't know, let's say Samuel is pulling you over And he's convinced that just by looking at this information, you were speeding. And he knows that in this area, the speed limit is 50 miles per hour, right? He's like so confident on this. And what he can use to prove that is say, okay, let me use the mean value theorem, because we're gonna assume that you're going continuously, you're not like stopping randomly, and your movement has to be continuous. So we'll say, okay, by the mean value theorem, if in the range 1 to 3 there exists an f of prime of c such that your speed would be 130 minus 50 over 3 minus 1, which is equal to 80. Did I mean 130 here? Oh, I wrote this problem wrong. Ignore that. This was supposed to be a 1. I had notes for my problems. This is supposed to be a 1 here. That's why I looked wrong. Apologies for that. But here, let me write this first and then explain. So what we have is x of t is a function of your position with respect to time. So the average rate of change would just be your average speed along that time. So from x equals 1 hour to x equals 3 hours, our average speed we calculated was 60 miles per hour, right? By the mean value theorem, since our speed, we're going to say it's continuous and differentiable. Because our function is continuous and differentiable, there must have been some point between 1 hour and 3 hours where your speed was equal to 60 miles per hour. And if at any point your speed was equal to 60 miles per hour, then you were exceeding this 50 mile per hour speed limit. And thus you were indeed speeding. And that concludes kind of, oh, again, apologies for that silly mistake there. But that concludes our mean value theorem. So next up on the list is kind of describing what implicit differentiation is. And this is the first thing that's not really a formula or a theorem. This is more of just a technique that, especially when you're dealing with multivariables, multivariable calculus, is going to be something really important. So let's start off with kind of this example. Y equals sine x. What is dy over dx? And from this, you're probably thinking, okay, this is just cosine x. That's easy. What's your point? Point being is that we have y easily in terms of x, so we can just use all the different rules, all the different memorization tricks that we learn, and we can just differentiate easily as that. But the issue is, what if we have this different equation, xy plus e to the y is equal to sine x, right? Let's say we have this equation here. Now, the issue with this, I'm going to rewrite this y because it looks like a 4. The issue with this is that we don't really have an easy way to represent y in terms of x. We probably could, but it'd take like a lot of really weird functions. So what we're going to do instead is we're going to differentiate the left and right side and use a process called implicit differentiation, where we treat y as kind of a separate entity to x and its derivative dy over dx is unknown. This is kind of better if I show you an example. So on the right side, we'll just say that this is equal to cosine x. Easy as that. Derivative of sine x is cosine x. Now, let's say we're taking the derivative of xy. Now, since y isn't a number, y is like a function, kind of just like x. So we actually have to use the product rule here. So we would say that the derivative of xy is equal to x times the derivative of y plus y times the derivative of x, which we know that the derivative of x with respect to x is just going to be 1. So we'll just leave it like that. And then we're going to add this to the derivative of e to the y with respect to x. And again, since y is a function, we have to use chain rule here, right? We can't just simply say this is the derivative of e to the y is e to the y. You would say that this is equal to taking y and plugging it into the derivative and multiplying by the derivative of y. So dy over dx. Now, what we can do is let's factor out that dy over dx. So we have dy over dx times x plus e to the y plus that leftover y is equal to cosine x. And when we move everything and divide, we would end up getting that the derivative of y with respect to x is equal to the cosine of x minus y over x plus e to the y. So we have something like this, and this is really helpful because number one, now we have this function kind of in terms of x and in terms of y. And many problems, you may be given a problem that asks you to find the slope at some point, and they'll either give you the x or y, or they'll give you one and you have to solve for the other before you can plug it in. This trick is really cool. As you can see, we don't have to worry about, oh, how am I going to isolate this y? Where do I use ln to get out of this? Do I have to use any other really random functions I need to Google? Instead, we get this really clean version of dy with respect to dx, or at least as clean as we can get with that problem. So let's erase this, and we're going to be talking now about maximization questions. Maximization. And this is kind of an easy concept that I'm just going to quickly breeze through, because to be honest, you could honestly solve this in like algebra 2, like with just algebra 2 or pre-calc knowledge. But the idea with maximization is sometimes we have a function that we want to maximize in context of a problem. So let's say we're trying to build a rectangular fence, and we know that we have this barn here, which has like some infinite length, right? So its length doesn't matter, and we want to construct a barn fence that connects to this barn. So we'll use part of this as a side. So our fence, for instance, could look like this, where this would be a width, this would be a width, this would be our length. And what we're told is that we have at most 60 feet of fence. So like the perimeter of the fence we're using is at most 60 feet. What is the maximum area that we can create? So what we can say here is if w plus w plus l equals 60, because that's all the fence we're using, we say 2w plus l is equal to 60, and thus we can say l is equal to 60 minus 2w. Now area is l times w, and plugging it in, we have w times 60 minus 2w, right? And then what we can do here is we just need to find the max of this. And if you're in algebra 2 or pre-calc, you'd recognize that, oh, we can just do 60w minus 2w squared. We just use negative b over 2a, plug it in, find the width is, if I remember right, this is like 15. And then you find the area, and that ends up being like 450, right? And then we're done, right? And even though that's helpful, obviously for this, another way we could do this is find the derivative of this function with respect to w. And the reason why is that if we're asked to maximize a function, that means that our function is probably going to look something like this. And anytime we have a max, we see that our point right there is going to have a flat slope. And this means that our derivative with respect to x or w or whatever our function is equal to 0. So that's one way we can do it. And this is especially helpful when we have more complicated functions. Like, I'm not going to go into the details for how you can solve this, more of an exercise to try on your own. But let's say we have the same 60 feet, and we want to create a triangle and a circle with the fencing. And we want to find what's the maximum or the minimum, I'm not sure which exists. You find that maximum or minimum combined area. So you'd have to go through the whole process of, let's say, this perimeter is x, this perimeter is 60 minus x. You'd solve for the side in terms of each of those, find the area, so x squared root 3 over 4, and then pi, I guess this would be r instead, pi r squared, add these, and then you would find the minimum or maximum. So I'm not going to go into details for that, but that's your general kind of overview as to how maximization works, or a review of it, and how differentiation can play a role in it. Last topic to really cover in terms of applications, at least applications we should definitely know in terms of the Calc 1 aspect, is going to be our common differential equations. So our Diff Eqs, right? And what a differential equation is that it's just some equation that has a differential. So for instance, something as simple as this is a differential. And one of the biggest topics, especially in Calc 2 with all the integration, is being able to solve these. So for instance, saying that all the functions that satisfy this are equivalent to y equals x squared plus c for some constant c. Some constant C. And I know I wrote that really badly, but you can get the idea. So that's kind of just a quick overview as to what a Diff Eq is. So there are two main differential equations or types of differential equations that I'm going to cover. And these are two that are like common enough that you should definitely try to memorize these if possible. So the first one we're going to cover is the exponential. And what this states is, I'm going to use P and T, you'll see why in a sec, is that all exponential equations come in this form. dp, the derivative of p with respect to t, is equal to k, where k is some constant, times p of t. And this ends up being p of t is equal to p naught, or the initial p, times e to the kt. So here's an example. Let's say we're undergoing exponential growth, and we know that our initial population is 5. We know our population at 10 is equal to 50, and we know that it satisfies this uh, this differential equation here, and we want to figure out what's the equation for this. If we have this memorized, this becomes easy. We would just say p of t is equal to 5e to the kt. And since we know p of 10 is 50, we can say p of 10 is equal to 5e to the power of 10t, which is equal to 50. And we can solve, sorry, this should be k, 10k, because t is equal to 10. We can solve, and after we solve, we move stuff around. We end up getting, I believe, 1/10 times the ln of 10. And this would just be our k value. We plug in that value, and then we would end up getting a function for p of t. And then any other question we're asked, like, oh, what's the population at this time, or when will the population equal this, then we can just solve those easily. The more complicated differential equation is going to be what's known as the logistic function. And if you've taken like AP Bio, for instance, you may recognize the name logistic function as like the S curve. And what that means is that most populations, rather than kind of going under this exponential J curve slope, so this is our exponential, it'll do something called a logistic curve, where it kind of forms this S shape and asymptotically approaches something called a limiting capacity, which is kind of like the max value it can reach. So in the context of biology, it'd be, oh, if we have only this much grass, this much water, this much area, then theoretically we can only support only this many animals or something. That would be an example of the limiting capacity. And what our logistic differential equation looks like is dp over dt is equal to kp times 1 minus p over L, right? And in this case, k is a constant, L is our limiting capacity, and p is our population function. And this is solved as p is equal to L over 1 plus ce to the negative kt, where k is the same constant. That's really important, that this k and this k are the same constant, and then c is a new constant that we have to solve for. And honestly, this is just like a mess of an equation, which is why it's really helpful to memorize this and not have to figure this out on your own. And whenever I cover what would it be, like partial fraction integration in the next video, you'll see that if you try to use that here, it's doable, but really, really annoying, especially under a time crunch. So I'll bring an example, and this example, I'm going to write a new color. This example comes from 2024 UIL region. And this is from problems 46 and 47 from the math test. So what you were given in this problem is that you were told that dp over dt for some population, I can't remember what it is off the top of my head, is equal to 0.00003 p times 5,000 minus p, where p of 0 is equal to 1,000, right? And you will notice immediately that this looks very, very close to our function right here. So since we want p divided by something and we want this to be a 1, let's divide this section by 5,000 and multiply this by 5,000. If we do that, we can rewrite dp over dt as, and I'm going to make sure I do this right. So this would be 0.15p times 1 minus p over 5,000. And this already tells us a few things. Number one, we now know the k value, and we know that our limiting capacity is going to be 5,000. So if we solve this, we get p of t is equal to 5,000 over 1 plus c e to the negative 0.15 t. Now, to figure out what the c value is, we note p of 0 equals 1,000, right? Well, we plug in p of 0 to be 1,000, we get 5,000 over 1 plus, and we note that e to the power of, when this turns into 0, e to the power of 0 is just going to be 1. So this is 1 plus c, which implies that c is 4. So then, once we just replace that with a 4, we have a complete equation. And then we could solve the rest of the problem, which I believe was just find the population at this point and also find the point of maximum growth. Point of maximum growth, fun fact, is going to be the point right here. So if this is L, the limiting capacity, the point of max growth is going to be right at L over 2, right when it kind of reaches that equilibrium point. And I believe that's the last kind of major application that you need to know. Really quick before I end this video, I am going to cover something that's a bit of a bonus. It'll sound a bit confusing at first, especially because this covers some integration techniques, but I'm going to cover a bit more as to those, where's my pen? Those differential equations and how we can solve for these. One of the easiest ways to solve differential equations is something known as separation of variables. So let's take the following equation. Let's see. dy over dx is equal to y times the cosine of x, and we're told that y of pi over 2 is equal to 1. And now we want to solve for a general, or the specific equation for this. Since this problem involves integrating, we're going to have like a plus c at the end, where c is some constant. So whenever we solve this, we normally get a general form of the solution. And then when we have a specific point that we know and we plug it in to solve for c, that becomes the specific solution. So how separation of variables works is we essentially want to move our stuff around. So we have dy on one side and dx on the other. In this case, we can multiply this dx to the right and divide the y to the left, and we would get dy over y is equal to cosine x dx. And then, actually, I want to keep this in black. Let's do that. So then the idea for this would be that now we can integrate each side. And again, I know I haven't covered integration yet, so I'll skip over it and just kind of just go with it. We end up getting that the natural log of y is equal to sine x plus c. And remember, since c is a constant, I can put the plus c on the left, on the right, or both. There's no reason to put it in both, that's just silly. But we can put on the left side or the right side, just depending on which one seems more convenient. In this case, I'll put on the right. So if we have this equation and we did solve this for y, which would just look like, I'll write this to the side, this would just be y equals e to the sine x plus c, or if we let k equal e to the c, we could rewrite this as ke to the power of sine x, and we would be done, right? However, we are given this specific equation, so if we plug it in, we get the natural log of 1 is equal to the sine of pi over 2 plus c, and thus we would get, we know this side is 0, sine of pi over 2 would be 1, I think. Yeah, sine of pi over 2 is going to be 1. So then c ends up being negative 1. Sorry, I'm like paranoid checking. I swear the sine of pi over 2 is indeed 1. Yeah. I have to like do the manually visualize like the unit circle every time. I have not gotten this memorized yet. But then once we have that and we plug it in, this would get us that the natural log of y is equal to sine of x minus 1. And thus y is equal to e to the power of sine x minus 1. And we just have an equation just like that. So that is separating variables. And then this is moving all the y's to one side, moving all the x's to the other side, and then just integrating each with respect to y or with respect to x. Second thing I'm going to cover is something called Euler's method. Euler's method. And this is a way where even if we don't know how to integrate it, we can use this method to approximate values. So let's say we're given dy over dx is equal to x squared plus y. We know y of 1 is equal to 3, and we want to figure out what y of 2 is. So the way we do this, I'm going to draw this table that our calc teacher used to use. So we have the x column, the y column, the dy over dx column, and the delta y column. So we'll write this out. Our first point is just going to be 1, 3. And here we would incrementally increase or decrease x until we got to our target. So in this case, I'll use what's called a step size of 1/2. The step size in every problem you do this in, you'll be given the step size. So this isn't something you have to come up with on your own. So we would use a step size of 1/2 to get to 1.5 and then 2. So our first step is going to be taking this x equals 1 and y equals 3 and using our dy over dx equation to solve for the instantaneous slope. In this case, it's 4. Then we would find the change in y. So since we're stepping forward by 1/2 in the x direction, we multiply 4 by 1/2 to get 2, and then we just add this to our starting y value. And then we would just keep doing this as many times as we need. So 1.5 squared is 2.25 plus 5 should be 7.25. Half of that would be 3.625. Add this here, and we get 8.625. So then we can say that using Euler's method, y of 2 is approximately 8.625. And then obviously if you make our step size super small, like let's say we made this like 0.001, we would get very, very close to the actual value if we just took the actual function and plugged it in. And then our last bit, this is already kind of a bonus section, but this is an even bonus section, something known as the integrating factor. And the integrating factor is something that I sort of learned in my senior year of high school when I was taking IBHL Math 2, just kind of on my own. But I didn't really use this a lot until both my college calc course and last minute grinding for UT's integration bee. But how the integrating factor works is that if we have an equation in the form dy over dx plus the function p of x times y is equal to q of x, then we can solve this using the integrating factor. And I'm not going to go through the proof for this, but if you are interested, I would recommend searching this up. You won't use this in BC Calc, you won't use this in UIL, but I think it's still pretty interesting how this works because it kind of just seems like magic until then. So we're going to use an example. We'll say that we're trying to solve the following function. Dy over dx plus 3 times x squared times y is equal to 6x squared. So our first step here is we're going to identify p of x. And p of x here is going to be that 3x squared. And we're going to calculate what is e to the integral of 3x squared. And this would be equal to e to the x cubed. You'd have a plus c here, but we can actually just set that plus c equal to 0. There is a reason behind that again just comes up with just Googling how the proof works. And basically, this c will eventually get canceled out anyways. Once we have this, we're going to multiply each of these sides by e to the x cubed. So we'll say e to the x cubed
times dy over dx plus 3x squared y is equal to 6x squared times e to the x cubed, right? And now here's where kind of the whole magic part comes in. If we integrate each side, integrate this side with respect to x, integrate this side with respect to x, with respect to x, what's going to happen here is this will actually end up being equal to e to the x cubed, which is known as our integrating factor. Integrating factor. This integrating factor times y is going to be equal to this integral here. And then once you learn about u sub, which is kind of just the reverse of chain rule, this becomes a very easy equation. This should end up being 1/2 times e to the power of x cubed. If I'm wrong, that's my fault. Actually, I should do this in my head, like before I do. This would be 2e to the x cubed. My fault. So this would be, 2e to the x cubed plus c. And then once we divide each side by e to the x cubed, we get y equals 2 plus c over e to the x cubed. And then we have this general solution here. So again, that was kind of just a bit of a bonus on top of that. You won't need to know this. But I mean, math is interesting enough that I am going to try to cover those kind of extra things as much as I possibly can.
Okay, to be honest, I don't know how many people actually watched all the way to the end. I'm assuming a lot of people skip through. But if you are watching like this kind of ending segment, thanks for watching. I put like a decent amount of effort into this. Alright, I'd like to say, considering I've never YouTube before, a significant amount of effort into this. And like I said at the start of the video, feel free to comment if y'all have any other topics. I'm gonna be around for um like a couple of more days, so hopefully I'll be able to use my sister's iPad more for these kind of hand-drawn videos. I really liked using it, and like her Apple Pen for the whole writing process really just detailed everything out, and it's way better than having to write stuff with like a mouse or a trackpad. So expect the quality of the videos to slightly worsen in a couple of weeks. But yeah, thank you for watching. Feel free to subscribe, like whatever. I'm not like professional in this, but yeah, see y'all.